So, like I said, glucose is one of the most important molecules, and it's if I were to commit one to memory, that's the one that I would know because tons and tons of things are going to stem off of that. So, if we look at beta D glucose right here, well, that beta D glucose can undergo a number of different modifications. For instance, beta D glucosamine, where we've replaced the hydroxide group on carbon number 2 with an NH2. Now that NH2 can serve as a foundational building block for a number of different molecules. For instance, N-acetyl beta D-glucosamine, well, that's going to have modification on that NH2. Now, glucosamine can be utilized to produce muramic acid, where we have a modification on carbon number 3's hydroxide group. And that can subsequently, that modification is this guy right here. We can also make from that N-acetyl muramic acid. So there's just a number of different derivatives and modifications that you can have with the foundational molecule of beta D-glucose. Now, this is something that is important for proteoglycans, and I'll get into that a little bit later in this chapter, but I just wanted to give you a little bit of an introduction that there are tons of different derivatives or modifications that can be made from simply a glucose molecule or a glucose or beta D, glucose 6-phosphate molecule, where we have a phosphate that has been added in place of the hydroxide group on carbon number 6. Okay. Now, reducing sugars have a free anomeric carbon. What that means is that it is not involved in any sort of bond. What's significant about these is that that aldehyde can be used to reduce something like carbon 2+ to carbon 1+. This is commonly used in analysis of the presence of glucose in urine, for instance. So if that aldehyde is present, well, that can also be used in the Tollens test to take Ag+ to Ag0. So this allows for detection of reducing sugars like glucose. And so, yeah, that's something that's done in clinical lab settings. Now, the alternative to a reducing sugar, or maybe not necessarily the total alternative, but a glycosidic linkage is what's commonly found between two sugar molecules, or two or more sugar molecules. This glycosidic bond between an anomeric carbon and a hydroxyl carbon. The glycosidic bond between monomers is more stable and less reactive than the hemiacetal at the second monomer. The second monomer with the hemiacetal is reducing. The anomeric carbon involved in the glycosidic linkage is non-reducing. Okay, so what that means is when you look at a disaccharide, which is two sugar molecules, two sugar monomers that have been combined together, you've got a reducing region and a non-reducing end. So disaccharides can be named by the organization in linkage or a common name. So the disaccharide formed upon condensation of two glucose molecules via a 1,4 bond is described as alpha D glucopyranose to 1,4 alpha D glucopyranose. The common name for this is maltose. Now, on the previous slide I said alpha D was the second sugar, but that's incorrect. It's a beta D glucose. So here's what we've got. Glucose. We've got the hemiacetal, we've got an alcohol. Previously what we were talking about, the cyclization formed that hemiacetal. So we've got alpha D glucose and beta D glucose, both with hemiacetals present. Now, what we're going to see take place is a condensation reaction where our hemiacetal is going to react with the alcohol to form an acetal. Okay, so the result is this maltose molecule where we've got alpha D glucopyranosyl 1,4 D glucopyranose. Now, what you see there is we've got a couple of things that are indicated. One, these are both D sugars, okay? They are both glucose molecules. Now, the result here is a bond between carbon number 1 and carbon number 4 of our alpha D glucopyranosyl and our alpha D glucose and our beta D glucose. So to use that last molecule that we looked at, that maltose, I want to compare that to this lactose molecule. This lactose is displayed as the beta form. Okay, now why is it the beta form? Well, what do we have here? We've got a glycosidic linkage between an anomeric carbon and an alcohol. We have carbons number 1 and carbon number 4. What's important about this is a beta sugar based on the fact that our anomeric carbon's hydroxide group was going up. And then we've got the alcohol's OH group on carbon number 4, which was pointed downward. We have this kind of curly Q, arguably kind of ridiculous looking bond there because of the fact that, well, it's all drawn in one line. Just for spatial preference, because the hydroxide group on carbon number 4 would be down and the hydroxide group on carbon number 1, since it's a beta sugar, would be pointed upward. Now, which sugar is which? Well, let's take a look at these. We have lactose. Let me go ahead and erase some of what I've already written. We know that glucose has a carbon 2 is down, 3 is up, and 4 is down for our hydroxide groups. If we look at this carbon on the left-hand side of our structure, we've got down, up, up. Okay, so that is not glucose. And if you look at the name, beta D glucopyranosyl, well, galactopyranosyl, that would be our galactose monomer. Now, the next sugar that's listed in our name is beta D glucopyranose. Okay, does our naming scheme fit? Down, up, down. Yes, indeed, that is a glucose molecule because we've got this that's present there. Okay, now what is our linkage? We have a beta sugar, our beta galactose forming a beta glycosidic linkage. But then we also have this reducing end out here. Our reducing end on our glucose is beta. What this means is that we could also have an alpha form of this sugar, where we would have a alpha 1,4 linkage rather than the beta. This being a reducing end means that our glucose can interconvert between alpha and beta. Now, what's going to happen there is that ring is going to open up. We're going to see a conformational change in that hydroxide group, and then our ring is going to close back up again. So that alpha versus beta interconversion is known as mutorotation. Okay, now the next sugar that we have, sucrose. Sucrose, what do we have going on here? Well, we've got beta D fructofuranosyl and alpha D glucopyranoside. Okay, what do we have there? Well, we've got a glucose and a fructose. And if you remember, fructose was basically the ketose form of glucose. Now, the way that this kind of shakes out is a little bit confusing because if you look at your name, beta D fructofuranosyl and alpha D glucopyranoside, well, the first sugar that we see is a 6-carbon sugar, or a 6-membered ring, which would be a pyranose. The second one is a furanose, a 5-membered ring. Okay, now you see beta D fructofuranosyl. Okay, so we're actually seeing the beta D fructose on the right-hand side, even though it's the first one listed. But look at this down here. we've got this sort of interconversion, this relationship here that's shown that these two sugars, whichever way you sequence them or label them, they're effectively the same. Now, what we have on the left-hand side is our alpha D glucopyranoside forming a glycosidic linkage with a beta anomeric carbon. Wait a minute. This is an anomeric carbon to an anomeric carbon. Oh boy, that's different. That's different than lactose and maltose, where we had these ends, these anomeric carbons that were kind of open and accessible. What that means is that this, let me circle them. This is different from this, specifically because that bond right there. And if you look down at the next one, trihalose, well, we have an anomeric carbon to an anomeric carbon. This forms what's known as a non-reducing glycosidic linkage. A non-reducing bond exists between these two sugars. So this is a non-reducing disaccharide. Okay, so it's very common to look at a reducing sugar and a non-reducing sugar. Monomers are all going to be reducing sugars because they have that functional group that allows them to interconvert between an alpha and a beta designation. That ring can open up and close again. When you have two anomeric carbons forming a glycosidic linkage to one another, they're not going to open up, or they're not going to be able to open up again, in which case that is a non-reducing disaccharide.